Hi, welcome to chapter number 8, Alkenes, Reactions and Synthesis. My name is Ramon Rios and I will guide you in this chapter. What we will do in this chapter, basically we will talk about how to prepare alkanes, a preview of elimination reactions, and then we will see the reactivity of alkenes, basically the halogenation with an addition of a halogen, halohydrins from alkenes, addition of hydroxy halogen, hydration of alkenes, addition of water by oxymercuriation, and finally we will saw the hydration of alkenes, addition of water by hydroboration. Okay, alkenes are very important in organic synthesis. As you can see in the slide, we can do a lot of reactions. We can transform an alkene in almost anything that we can imagine. Here I put some examples like the transformation of an alkene to an alcohol, to an alkane, to a diol, to a carbonyl compound, cyclopropane, epoxide, halide, 1,2-dihalide, or halohydrins. When we want to prepare an alkene, basically this reactivity is based in the elimination reactions. Okay, we have two options. The dehydrohalogenation, that means we have a halogen here, and we eliminate the halogen plus the hydrogen that is in the carbon alpha to the halogen, to the carbon that contains the halogen. Okay, basically what we are doing is the opposite reaction that we did when we was adding hydrogen bromide to a double bond. Okay, another common method is the dehydration. Basically we have an alcohol and what we do is to generate a double bond. Normally this reaction is working through the mechanisms. We have here the alcohol. Okay, we add acid, and the pair of electrons of the alcohol, the oxygen, is attacking the acid to generate this compound. What we do in this step? Basically, we are transforming the hydroxyl group in a water group. Why? Because a hydroxyl group is a very bad leaving group, while the water is extremely good leaving group. What is happening now is that water is leaving, is departing, and what we generate is this carbocation. Okay. This carbocation now can eliminate with a hydrogen that is positioned one carbon away of the carbocation. That means that we can remove with this proton, or with this proton, giving us, in this case, two different products, means this or this. Okay? This will be the two products generated by the elimination of this alcohol. If someone is asking, the tetrahydrofuran that you see in the reaction is a solvent that is basically a cyclic ether, a 5-member ring cyclic ether that is working as a solvent because it's unreactive as the major part of ethers. Okay, then what happened, for example, in problem 8.2, they said that how many alkene products, including EZ isomers, might be obtained by degradation of the free methyl free hexanol. Okay, again, what will happen is that first of all, we protonate the alcohol, forming water, the water is departing, and then what we generate is the carbocation. If I draw it well, what I will get is this carbocation here. And now this carbocation can eliminate with any hydrogen that is one carbon away of the carbocation. That means these three different hydrogens, giving us, for example, if we eliminate this hydrogen, we will get this or this, the E and Z. So, okay. If we eliminate this, we can only get one. And if we eliminate this, what we will get is these two. Okay? That means we can eliminate this carbocation, eliminate with any hydrogen that is one carbon away from the carbocation. And we have to consider that each elimination can give us the E and Z stereoisomers. Okay? Well, if we are talking about reactivity, we can talk about the halogenation of alkenes. Basically, it's a reaction between an alkene and a halide, bromine or chlorine normally. Okay? It's an addition reaction, and what is happening is that we have a double bond, we add a halogen, and we got the dihalogenation. One halogen is bonded to each carbon of the double bond. How is working? Well, in principle, we can think that the mechanism is quite similar to the addition of hydrogen bromide to a double bond. That means the pair of electrons of the double bond attacks the bromine molecule, taking one bromine, and in order to avoid breaking the octet, the bromine-bromine bond is going to the bromine, forming bromide and a carbocation. When we have the carbocation is attacked by the bromide to form the dibromination. However, these mechanisms doesn't explain our observation, experimental observation. For example, if we have a cyclopentane, we add bromine, what we will generate is only product the trans 1,2-dibromo cyclopentane. In any case, we will not see the cis 1,2-dibromo cyclopentane. If we are thinking that the mechanism is what I write before, obviously doesn't have any sense, because once we have the carbocation, we can have the attack of the bromide from up or from down. That means that we will generate the trans and the cis. If we only generate the trans, means that the mechanism probably is different than what we saw. The old explanation is the formation of a bromonium ion. Okay? Basically, what is happening is that the double bond is attacking the bromine. The same bromine is attacking the carbocation generated in situ, forming this bromonium ion. Okay? Once we have the bromonium ion, for example, in the case of the cyclopentane, because the bromonium ion has to be up or down of the plane of the cyclopentane, okay, the bromide has to attack from behind the carbon-bromine bond. This is due because this reaction is SN2 type. It's not real SN2, but it's a SN2 type reaction, okay, that lead us only a trans, because if the bromide attacks from the upper position like here, the only option is that we get is that the bromide is up and the hydrogen becomes down. Okay? What happens if we do this reaction with 1,2-dimethylcyclohexane? Okay, I draw the 1,2-dimethylcyclohexane. The first step is the addition of bromine. That means this attacks here, and this is going down. What we generate is the bromonium ion, that is this. Okay, I will grow it down, but you can grow it up or down, it's exactly the same. Okay, and if I grow down the bromonium ion, the two methyls becomes up. When I have this, basically the bromide has to attack the bromonium ion by the opposite side, where is the free member ring. Because this is a SN2 type reaction, that means that the attack is from behind. What we get if the attack is from behind is the bromine up in this carbon and the methyl down, and here just the opposite. The bromine down, that is where was the free member ring, and the methyl up. This attacks here, this is going to the bromine, and we generate the Kranz compound. Okay, this is the mechanisms. The mechanisms of the dibromination, the addition of halogen to a double bond. What is happening is that we form the bromonium ion. Oh, here I make a mistake because they say chloride, not bromide, but it's exactly the same. Change Br for Cl and will be the same. In the case of the chloride, we are forming the chloronium ion. Okay, but what happens if instead to use only a halogen, we are using halogen in water? Well, the first step will be exactly the same as you can see here. We add bromine, we are forming the bromonium ion. This is exactly the same. However, now, instead to be this bromonium ion to be attacked by the bromide, we have a better nucleophile. We have water as nucleophile, that is a better nucleophile. Water will act as a nucleophile, will attack the carbon in the same way that the bromide attacks before. That means opposite to where we form the bromonium to generate a Kranz compound. The OH attacks there, opens the bromonium cycle, the bromonium ion, and then simply we remove one proton to generate the final product, that is the addition of a hydroxyl group in one carbon of the double bond and a bromine in the other carbon of the double bond. Okay? That means it's the same reactivity, but instead to do the opening of the ring with a bromide, we have a better nucleophile in the media, that is water. Another possibility is the addition of water to a double bond. In this case, we have two options. One is to do oxymercuriation. Okay, basically, what we can do is we add mercurium acetate, then after this we do a treatment with sodium borohydride, as you can see, sodium borohydride, and what we get is the OH in the most substituted carbon of the double bond. Okay? Why is this? Well, if we do this, when we are doing mercurium, what is happening is that, first of all, we form something very similar to the bromonium ion. The mercurium is forming a free member ring with the two bonds, with the two carbons of the double bond, forming this mercurium ion. Once we have this mercurium ion, what is happening is that the water attacks this free member ring, again, opposite to where is the mercurium, and will attack the most stable carbocation. Why? Because this bond is very weak. The bond that we are forming is very weak with the mercurium. Okay? And then means that the carbon that stabilizes better a density positive charge will be the most accessible, because if stabilizes better the positive charge, this bond will be larger and weaker. Okay? That means the OH will always attack the carbon that can stabilize better the positive charge. And which is the one that can stabilize better the positive charge? Is the more substituted carbon of the double bond. Why? By the phenomena of hyperconjugation that I explained in chapter number 15. Number 7, sorry, not 15. Okay? Once we have the attack of the wedge in this position, we generate this hydroxymercurium compound, and then what is doing the sodium borohydride is removing the mercurium and putting a hydrogen there. That means with using this method, what we generate is the OH. We put the OH in the most substituted carbon. When this is happening, we say that this is a Markovnikov product. This Markovnikov product is when the OH is going to the most substituted carbon, or the hydrogen is going to the less substituted carbon. Okay? For example, if we are doing what product would you expect from oxymercuriation, demercuriation of the following alkenes? Well, in this case, what I will expect is that this position of the double bond is more substituted. That means that I will expect OH here, hydrogen here. In this case, this position is more substituted. What I expect is OH in the most substituted, hydrogen in the less substituted. Okay? Always like this with oxymercuriation, the OH is going to the most substituted position of the double bond and hydrogen to the less substituted. But you have to know that organic chemists, we like to control everything. That means if we can put the OH in the most substituted carbon, we want to have another method that allow us to put the OH in the less substituted method. And how we do this? Basically, what we do is a hydroboration. A hydroboration is the addition of borane to a double bond. Okay, I imagine that we have this double bond. Okay, this double bond we have, as before, one position disubstituted and one position monosubstituted. And this is approaching the BH3. The borane is approaching basically, if this is the double bond, over the p system is coming the borane. Okay, that is interacting with the pz orbitals of the double bond. Then, obviously, the boron is the bigger part of these two. This is bigger. That means that we'll approach to the smaller position of the double bond. That means the boron will form a carbon-boron bond with the less substituted part of the alkane, while the hydrogen, because it's smaller, will fit better in the bigger part of the alkene. That means that in this case, what we will get is here we will have the hydrogen, and here we will have the boron. Okay, here we will have the boron. Why? Because the boron is bigger than the hydrogen and will go to the position less aesthetic hindered. Once we have it here, okay, what is happening is that we add hydrogen peroxide and we transform the boron in a hydroxyl group. Importantly, this transformation of a boron in a hydroxyl group takes place in the same position where we had the boron. Why this is important? This is important because, for example, if we have a cyclic compound like here, okay, we know that because this double bond has different constitution in each carbon, the first step will be the formation of this. Where the boron is in the less substituted position and the hydrogen is in the most substituted position. And importantly, as the boron and the hydrogen will take place addition by the same site. Okay, that means if the boron is up and the the hydrogen will also be up. And then what is happening is that we transform the boron in a hydroxyl group by adding hydrogen peroxide. That means we draw the same that we had, but instead of the boron, we put OH, and we keep the same. The hydrogen and the methyl. Okay, again, the boron will attack the position less substituted. And the addition of the boron and the hydrogen will take place by the same site of the double bond. The next step is we substitute the boron by OH when we treat the boronate with hydrogen peroxide. That means that we will always get the non-Markovnikov product, and the OH and the hydrogen and the OH will come in the same phase, okay? Giving us the anti-product or the Kranz product, okay? It's important that we remember this. Here you can see a very nice example of the mechanism, very well ground. Okay, here is the addition of the borane. The borane is coming from perpendicular to the plane of the double bond. Okay, it's interacting with the pz orbitals. And the hydrogen will always go to the most substituted carbon in order to avoid the steric interaction between this group and this group. The two big groups has to be far away one of the other. Then we generate this with the hydrogen and the borane. Check the hydrogen and the borane in the same site of the double bond, in this case both down, but you can draw both up, it's not a problem. And then what is happening is that with hydrogen peroxide, we transform the boron in a hydroxyl group, but always keeping the same configuration, as you can see here. That means that we will get the Kranz 2-methyl cyclopentanol. Okay? We can do the following problems. Show the structure of the product that you will obtain by hydrogenation oxidation of the following alkenes. Okay, in this case, what we will get okay, first of all, the borane will go to the less substituted. That means that in the most substituted, we will put the hydrogen. And with the most substituted, we put the boron, and will transform in an alcohol. Here, we will do exactly the same. What we will get is we put the hydrogen here, and the boron in the other carbon, and then we transform the boron in a hydroxyl group. In this case, exactly the same. I will draw the intermediate. Okay, I put the boron up, and I put the hydrogen up. Okay, I add the boron and the hydrogen for the upper phase of the methyl cyclohexane. That means that the methyl is from below, and I put the hydrogen in the most substituted position, as you can see here. Once I have this, I add hydrogen peroxide, and I transform the boron in a OH, keeping the same configuration. That means I will get this compound. Okay? Good. I hope that you understood the mechanism, because in this chapter all are mechanisms. Please repeat it. Please try to understand how it's working. Why it's working also is very important. And if you have any question, please feel free to send me an email or come to my office. Okay, remember the study questions for problem-solving sections. In the textbook of McMurray, in chapter 8, you can do all this exercise. All the answers are in Blackboard. I did all the answers. I put it in Blackboard. And please read the textbook, chapter 8, 1 to 5. Thank you very much for your attention and see you in the next lecture.